The international working group has developed an analysis and interpretive framework that we're hoping to publish very soon so we can help other labs implement this in a standardized way. And while no technique will perfectly detect all possible abnormalities, many published studies have already demonstrated that OGM is a better frontline test for hematologic malignancies. And I just basically want to leave you with a couple of examples. There certainly are some more. So this is general hematologic malignancies. This is acute myeloid leukemia. This is myelodysplastic syndromes, and this is B-cell acute lymphoblastic leukemia and T-cell acute lymphoblastic leukemia.
What up, investors? It's your boy Dayo. Welcome to Frunkla Investment, where I talk about Bionano Genomics on a daily basis. From Sunday to Sunday, I try to post at least one video. Always do your own due diligence. Don't sue me, bro. Let's get to it.
So I want to conclude there. I just wanted to basically say that our current lab practice really requires us to use a lot of different technologies to help us get at the biomarker requirements for hematologic disease. That's not going to change because we're still going to have to do NGS or other type of PCR tests, etc. However, OGM is emerging as a tool that can really collapse a lot of the conventional cytogenetic techniques such as karyotype fish microarray MLPA that we're using for copy number assessment and sort of to get at some of the problems of ambiguity that I talked about at the beginning, where you know your karyotype gives you so much information and you need a fish to resolve it or you need something else to resolve it. And so OGM is really an interesting tool in that sense. The international working group has developed an analysis and interpretive framework that we're hoping to publish very soon so we can help other labs implement this in a standardized way. And while no technique will perfectly detect all possible abnormalities, many published studies have already demonstrated that OGM is a better frontline test for hematologic malignancies. And I just basically want to leave you with a couple of examples. There certainly are some more. So this is general hematologic malignancies. This is acute myeloid leukemia. This is myelodysplastic syndromes, and this is B-cell acute lymphoblastic leukemia and T-cell acute lymphoblastic leukemia. And I'd just like to acknowledge everybody in my group, Bionano, the international working group, and also say that we have an OGM special issue for anybody that's working in this area and that would like to contribute papers, that we're accepting papers until the 15th of January, 2023. And at that point, I'm going to finish and open for questions. Thank you.
Oh, well, that was wonderful. Thank you very much indeed, Adam and Alka, for those two respective talks. Very stimulating and teases up very nicely for our Q&A. And with that, we're now going to transition to the Q&A discussion. So we'll be right with you momentarily. So we have some questions here that I can put to Adam, which is fantastic. Adam, I'm sure you'll be happy to answer some of these, hopefully. So I will fire away. So we have a question here that's come in, and it says, there was a recent publication that claimed that short-read genome sequencing could be used to replace karyotyping for myeloid neoplasms. Is there an advantage to performing short-read NGS versus OGM?
Hi, Damien. Thanks. Can you hear me okay?
Yeah, no, that's good. You're loud and clear, Adam.
Wonderful. Okay. Yeah, that's a great question. I mean, I think the first thing I really just like to point out first is that one of the things that we're sort of now talking about largely in this community is that for many years, we've sort of had this very technology-centric classification for hematologic malignancies, which has revolved around, karyotyping. And so the whole classifications have been developed based on, karyotypic observations. And the idea now is we need to move away from this technology-specific classification to a more technology-agnostic classification that deals with the underlying biology, which really opens up the possibility to use multiple different techniques in order to be able to look at these kinds of abnormalities. And that's I think where we're seeing a lot of these publications with different types of testing strategies. And a lot of these, again, it comes back to the paper that I mentioned, that there's going to be financial and logistical and technical and medical questions that each lab's going to have to answer independently about how they're going to they're really going to deal with the testing in the lab, and some of those could be, geographical even, whereas, like certain countries, like in Europe or Canada or the United States might make different decisions about testing based on, what kind of resources they have. And so ultimately, for the short read question, I think it's a very interesting technology, certainly in the way that it was published, if I'm recalling the publication correctly, which is, I think it was Duncavage et al. In New England Journal of Medicine. There were a few things that I think, and one was that, really they were only doing 40 to 60x coverage. So you don't have a really huge amount of coverage, in comparison to OGM, where you have, 300 to 400x coverage usually. And it's only designed to detect known rearrangements, and it has a lower limit in terms of size detection for CNVs of about 5 megabases, which is in line with sort of G-banded karyotyping at the current time. Not necessarily every case, but good quality cases for sure. So it certainly has some advantages because it's going to detect those cryptic rearrangements, those known cryptic rearrangements, and things that you can't see with karyotyping. And then you have to consider the cost. So that level of sequencing is not cheap, and so you do have to have a fairly significant sequencing infrastructure in order to be able to run it. So it may not be a decision for all labs. So again, I think it really comes down to the question that there are some, what tests are you going to run alongside that to make sure you're getting all your SNVs, your single nucleotide variants that you need to get. And again, there's another good publication from Augusta University, also Nikhil Sahajpal et al., where they actually look at this question in more detail in their paper, where they use a combination of OGM with an RNA-DNA panel, a sequencing panel at high depth, to look at diagnosis for myeloid malignancies. And so there's a lot of considerations, I think, but everybody needs to weigh those decisions in their lab and figure out what works best for them.
Okay, that's a great answer. So what I'm getting is sort of we need a new taxonomy as such, but also, as you rightly say, it's going to be pretty dependent on individual needs, size of the lab, what you're testing for, how you scale it, how you implement it. So that will be different between individual institutions. So no, that's great. Thank you for that, Adam. That's brilliant. So next question that's come in. Can you ever use formalin-fixed paraffin embedded material?
Yeah, so OGM requires high molecular weight DNA, and so sort of the average length of molecule, sort of needs to be in the sort of 200 kilobase type window in order to sort of build these genome models, and so sort of the assemblies. So if you look at DNA from paraffinized tissue, generally you're looking at fragment sizes sort of between 500 base pairs and 10,000 base pairs. So paraffinized DNA is generally much too short to use for OGM. Now, I'm sure there's lots of things that there maybe could be done. I'm just at the current time there just is no solution for using FFPE material for OGM.
Okay,
but you can use fresh frozen, so that's the alternative. If you are interested in solid tumor analyses, fresh frozen is an option.
Okay, great, thank you. Next question here: when will OGM have a CPT code?
Yeah, ask the Canadian the CPT code question. I don't know 100%. I do know I have colleagues in the U.S. that have submitted applications for CPT codes. And as I understand it, it wouldn't be a single CPT code. There would be CPT codes based on applications, probably, if I understand how the process works correctly. So, there might be a CPT code for myeloid cancer. There might be another one for say, FSHD, like Alka was talking about. So, yeah, I know that there are many labs that are in the works for getting CPT codes coming. I just don't know exactly when they would be released.
Right, okay, fair enough. question coming in here saying you spoke about some of the problems with varied techniques. Can you comment on problems that you might run into with OGM?
Yeah, sure. I mean, I guess if we're talking about, you know, like looking at the gamut of testing in the laboratory and what are the, you know, I pointed out some of the problems with our current workflow. What are some of the issues that we do see with OGM? So some of the sort of things I think I said right up front in my talk, the advantages of karyotyping. One of those big advantages is that karyotyping is single cell. So it's able to you're actually able to see those structural abnormalities on a cell-by-cell basis and sort of build up clonal architecture. So it's important to remember that OGM is a bulk DNA technique. So it kind of mashes exactly like all other sequencing-based or molecular bulk DNA-based techniques do, is that they sort of mash all that stuff together into a single analysis. So, you know, we can get some clonal architecture off of OGM, for example, by looking at variant allele frequencies. So if, you know, you see a variant allele frequency, you know, at 0.45 or 0.46, you know, that's pretty much in everything. And then you see, you know, another variant allele frequency that's much lower, you know, you can probably assume that's a subclone. So we can sort of recapitulate some of that information, but it's not as detailed. The clonal architecture isn't as detailed as it is with techniques that are you know, single cell based like karyotyping. And so there are some other things. There are a couple other things there. Things like polyploidy is so if you have a mix of normal diploid and polyploid clones, it's difficult to sort those out with OGM. And then the other thing that is quite difficult to see is rearrangements that involve the repetitive DNA of the telomere or the centromere. So these would be things like balanced whole arm translocations, or even to some extent, so an unbalanced whole arm translocation you would see as a copy number imbalance, but you wouldn't see the mechanism. You wouldn't see that little line on the surface plot going from the centromere of one chromosome to the other, because it's not looking, the technology doesn't look at those highly repetitive sequences. So those are kind of the major things. I mean, in terms of how relevant that is in cancer analysis, you know, because what's really relevant, say, to an unbalanced whole arm translocation is the copy number imbalance. So you're still getting that information.
Okay.
And so, you know, all of that stuff kind of has to be weighed in the overall big picture of the gains and losses, not the copy number gains and losses, but the gains and losses of those techniques. So, like, we can see things at much higher resolution, like the cryptic translocations and the prognostic or predictive translocations that are really important for treatment decision making, which may not be as easy to see with the conventional techniques. And also, all that being said, at the end of the day, you know, there's nothing that says that, you know, we can't do one test as a frontline and then have another test on hand as a backup, which we already do today, right? We do karyotyping, then we do FISH, then we do microarrays. So there's no reason we're not necessarily talking about throwing all of those techniques out. We're just saying we might switch the order around, or, you know, do some less, obviously, than we're doing now. But anyways, I think that gets to the point of the question.
No, that's a great answer. Another one here says, was wondering your thoughts on other mapping technologies, i.e. mate pair sequencing, Hi-C, etc., pros and cons.
Yeah, so Hi-C, as I understand it, is a chromatin mapping technique. So I'm not sure that sort of would compare. That is sort of a different level. I would be more thinking about sort of genome level epigenetic changes as opposed to actual structural variation. And mate pair, you know, again, mate pair was a really interesting technique. I'm not sure if it's being run clinically anywhere. And, you know, again, I mean, it's this whole question about adoption and logistics. So, you know, like if it doesn't enter the sort of the mainstream, then we have to sort of ask ourselves, you know, why are those things not in the mainstream then? I know there are a couple of other like flavors of mapping, like not optical mapping, but sort of other type of genome mapping technologies, where there were companies developing things like that. But I don't know of any that are well developed at this time.
Okay, good stuff. Well, there's a few others that have come in here, which you probably actually you're privy to those too, of course. Now, there's one question here that's been asked about time, so I'm wondering if that's an easy one for you in terms of turnaround time. As you can see those, Adam.
Yeah.
What is the OGM testing's turnaround time? 1 day, 5 days?
Right. I mean, turnaround time is obviously dependent on a bunch of factors, right? Because it depends what you're looking for. It depends. There's a couple of different actual run times in the flow cell and the bioinformatic time that's required in order to do the computation. So, but in general, you can go. It's easy enough to say you can go from sample to a final analysis in 4 to 5 days. Whether you're going to report your final analysis, quickly is going to depend on a lot of internal lab factors. Obviously, that do you have a pathway to report stuff quickly? Do you have enough people, etc.? But I mean, it's conceivable. It's very conceivable to be able to produce a full genome report in 5 business days.
Right. Okay. Okey-doke. What about that question there, Adam? Does that resonate? Is that something you can answer? The 1481 there at the bottom.
How do you do the filtration of the results?
Yeah. Is that something you can answer, or is that something?
Yeah, sure. I mean, we currently have a software tool that comes with optical genome mapping. It's called Bionano Access, and it allows us to do a lot of different types of filtration of the data. So obviously, when you do a control like normal sample, we do see SVs that come up routinely, and obviously more than you would see on a karyotype analysis. Lots of smaller SVs, and so there's a couple of things that we have. So there's a standard control database, 300 patients that you can filter against and say, I don't want to see any sort of stuff that shows up in more than say 1% of the general population. So you can get all that sort of common variation. You can eliminate that right away. We can also use gene list filtering, or you can use size filtering. But I think the gene list filtering is actually quite interesting. So you say, for example, you're looking at hematologic malignancies. You could take a list of genes that's specific to hematologic malignancies, and you can then filter against those. So you can very quickly identify genes that potentially have impact in those diseases. Okay, great stuff.
Unless there's anything else there that's screaming at you, Adam. I mean, there might be maybe one more in there potentially, although you might have partly answered that. But I think we've pretty much answered most of them, other than maybe you did answer that one in part. Can OGM detect different clones? Can you comment on how to do this OGM? I think you may have.
Yeah, I think we touched on that. I mean, I think one of the interesting things, I think maybe just in closing, I can deal with the workflow question to some extent, is that what's really interesting is that in the lab we have to deal with a lot of different diseases, and we have a lot of the high sort of incidence, high frequency stuff that comes in all the time. We develop probes for, we have ancillary assays and all our tools developed, but we do actually see a lot of rare hematologic malignancies that we don't have a lot of tools for, generally speaking, and diseases that are more difficult to analyze sometimes just because of the location. I mean, one of the prime examples would be like myeloid sarcoma, for example, and OGM actually provides us really interesting opportunities for these and more esoteric types of hematologic malignancies, like a T-cell disease, and where a lab may not have a full host of FISH probes stocked, for example, where we can actually now do a really high resolution genome analysis. So, I mean, I think certainly for us, we're looking at very quickly moving to an OGM first workflow for most hematologic malignancies, to provide that really whole genome picture and high resolution. And then when we see certain things, then decide whether or not we need to reflex to different types of assays. If we need to, say, confirm a polyploid situation, if that was clinically relevant, for example, have to do a reflex karyotype, for example.
Right, I got you. Okay. Yes, because in many ways it's still early days, and you're trying to build the infrastructure, the framework, the methodologies, and it's going to take time. But once that's done, it's clearly going to have a huge impact. Well, listen, that's great, Adam. I think we've pretty much got through all of those, and you answered those very comprehensively. So a huge thanks to you, not only for your time and your great presentation, coming on and talking, and a huge as well to Alka, and of course Bionano Genomics, who was our sponsor, and for their support in producing this webinar, part of our Precision Medicine series. So just to let you know, folks, the on-demand link will go live in about 48 hours and will stay on the site for 12 months. It just leaves me to say we hope you enjoyed it today, and we look forward to welcoming you for some more Inside Precision Medicine webinars. With that, I wish you all a very pleasant rest of your day. Thanks very much.